start. This is Brian. Everyone knows Brian, right? Brian, do you need anything to plug? Do you have a job? Are you on the market? Hopefully not.
No, I'm very happy in my new job at Cal State Long Beach.
All right. So
all right.
So yeah, everyone join me in welcoming Brian.
Thank you. I am really excited about this talk. I gave like a 20-minute version of this talk at Math Fest a year and a half ago, which was nowhere near enough time. And so I'm glad we get to spend some more time together doing it. So, oops. Okay, so here's a proof. It's mostly from Weber and Alcock 2005 paper. The proof reads, 13 is prime. If 13 is prime, then 1013 is prime. Therefore, 1013 is prime. Please share your thoughts out loud or in the chat about this proof.
Well, I want to be convinced of line 2, but other than that, it seems okay.
Great. Justin, I do think that it is a sandwich. You know,
Yeah,
the first and last
sure
line with the middle one sandwich between them, I'm 100%. It's a sandwich.
I'm not sure about the filling in this sandwich.
Probably does not have an implication without a reason. Why is one derived from the other? If then, so why?
Great. So the consensus is that second line is a problem. Yes. And so I claim that you just did something pretty subtle, abstract, and cultural, and that there's a good chance you don't have words for exactly what you did, and that you can't, I at least couldn't, point to a mentor or a professor or anything actually talking explicitly about this ever in my education. And in fact, I think in practice, what happened is those of us who sort of successfully stumbled into the right register for handling this kind of language are the ones who stayed, and everyone else was like, "This, what are they doing? Why are they doing this?" And so that's sort of like the secondary claim, which explains the title. So we'll talk a little about at the beginning and then a little more, much more at the end, is that I don't think students can take ownership over their own mathematics if they can't decide for themselves if an argument is valid. Like if they don't have the authority in our space, or they don't have the power to decide if an argument is valid, then like none of the other justice objectives are gonna work out sufficiently. And that we need to support this kind of learning. So that's what this is. This talk is about how I use one particular math education research paper to try to help my students decide for themselves if they accept the truth of an argument. So we're going to talk a little bit more about that motivating cursed proof. Then we're going to what we're really talking about is called Toulmin Analysis. I'm going to talk through an example, and then you're going to do an example in breakout rooms. And then we'll talk about the pedagogical activity, how I actually use this in class, and then we'll sort of think big picture about how all of this works. So here's sort of the big picture of Toulmin analysis. Toulmin comes from the field of rhetoric. So this is sort of coming from outside math education, but in about 1985, education scholars were like, hey, this is really useful for understanding what's happening inside math classes. And so you analyze arguments by identifying conclusions or claims, figuring out what specific information you already have, data, that supports that. Those are connected via warrants, general principles that connect those two together. And sometimes those warrants need backing. So one way to do this kind of analysis of our work is like hypothesis, conclusion, the entire proof. And then the backing would be the proofs of any things that you cited inside your proof. And that's fine, but that's not the level of specificity that we think about this most of the time. But when people do like really high-powered Toulmin analysis talks, these things get nested within. So something that was a conclusion before can become a warrant later because it's being used as a general principle. So you get these sort of like nested inside each other diagrams. So let's go to that cursed proof from the first couple of minutes. I see that Keith is here. Hi, Keith. So this is all from the Weber and Alcock paper. So one way to analyze that middle line is that the conclusion is this should be if 13 is prime, then 1013 is prime. And why might that be true? Well, 1013 is prime. And so one warrant we might give is it's an if-then statement, and the then is true, therefore the statement is true. So this statement is true. Right? Okay, and this is called the material implication, right? So what we're concerned with is the truth of each line. Another analysis of the same statement is that it's framed like 13 is prime is the data, 1013 is prime is the conclusion, and there's no overt warrant associated with it. And in their study, several mathematicians suggested that what they did was they tried to infer an implicit warrant. And the one that they suggested is that if n is prime, then 1000 n is prime, which is false, right? And that's why, just like Andrew said, that middle line is a problem. And that's why people sort of rejected this proof as having a gap in it. In the actual paper, they use 7 rather than 13 as the number, and 1007 isn't prime, which Keith has admitted that they didn't notice for several years after publication. And I didn't notice for several years of teaching this paper. It wasn't until I did this activity with my high school students that one of them, because they all had laptops in front of them, one of them was just went to Wolfram Alpha and was like, factor 1007, and it successfully factored. And I was like, oh my goodness. So that's kind of irrelevant. The whole point is that what the mathematicians did was that they tried to infer these general warrants. And because there was the one that they made wasn't acceptable, they rejected the proof. So I sort of claimed here that the material implication isn't what we're doing, but I also sort of want to, again, inspired by the paper, take the idea that the material implication is insufficient. So this is not quite the example from the paper, but it's structured in the same way. Here are 2 claims. Since 2 and 3 are greater than 1, 2 plus 3 is greater than 1. And since 2 and 3 are greater than 1, 2 divided by 3 is greater than 1.
Hang on, that's not what it says on the slide.
What did I say?
On the slide, you've got the 3 over 2.
Oh, sorry, 3 over 2. Sorry. Since 3 and 2 are greater than 1, 3 over 2 is greater than 1, is what I meant to say. The sort of like, just to write these as if-then statements, it's if 3 and 2 are greater than 1, then 3 plus 2 is greater than 1. And if 3 and 2 are greater than 1, then 3 divided by 2 is greater than 1. But if you were to try to make these into implicit warrants, then the first one is fine, right? I mean, we may not have justified it together, but does everyone accept if you add 2 numbers that are bigger than 1, you get something bigger than 1?
Yeah.
Great. But if you divide 2 numbers that are bigger than 1, do you always get something bigger than 1?
No.
No, right? So my attempt to make a general warrant out of this one is false. And yet, the material analysis of this structure, 3 plus 2 is greater than 1, and 3 divided by 2 is greater than 1, right? And so in terms of the material implication, they are both true. So what I'm trying to do with this pair of examples, which is again from the paper, is to show that the material implication is not sufficient for doing what it is we do as mathematicians. And I think I've already convinced you that we're more interested in whether an argument is warranted rather than whether that argument is a string of true statements. Right? That's what we're doing.
The mathematician saying that we turn both 3 into the same A.
Yes, there's lots of things we could have done. So this will come back again, but when you're looking for an implicit warrant, there is no algorithmic universal way to go about doing that. And that has implications about what the heck it is we do when we're doing mathematics. So absolutely, Kim, we'll come back to that. So Weber and Alcock have sort of said, this is what mathematicians are doing when they're trying to read a proof line by line to decide if they accept it as valid. It proceeds line by line, assuming that each new line is an argumentation whose conclusion is the statement being asserted. The reader identifies the warrant and the data used to support that conclusion, inferring them if necessary. They might be implicit. If the warrant is socially acceptable as applied, then the line is accepted as valid. If the warrant is false, then the entire proof is declared invalid. And if the warrant is plausible but not socially accepted, we sort of identify the proof as having a gap. So this is their description of how mathematicians read proofs. So let's do some together. Okay, see if I can make this work. There, this one. Okay, can you see the Pythagorean theorem now? Pythagorean theorem, it probably should be named something else, but let's do a Toulmin analysis of the Pythagorean theorem. So if a right triangle has leg lengths A and B and a hypotenuse like C, then A squared plus B squared equals C squared. So I'm going to read through looking for my first claim or conclusion. Suppose we have a right triangle with leg lengths A and B and hypotenuse like C, pictured below with those vertices. In previous courses, we learned that we can drop an altitude from any vertex of the triangle to the line opposite that side. So that's a claim. We can. So that's a claim. Oops. So that's my first claim. And why do I believe that's true? Well, in previous courses is framing as the warrant. That's me sort of saying that's the general principle. We learned this before. And when is that warrant valid? I have to apply this to a triangle. Right, so the data is that I have a triangle. The warrant is this previous theorem about dropping altitudes for triangles, and the conclusion is that we, in fact, can drop the altitude. The next claim, the point of intersection, labeled D below, must be on the segment AB. So there's several ways to go about thinking about this one, but I am saying here that labeling the point D is not a claim. Maybe sometimes students think that kind of thing is a claim, but I don't think it is. But the asserting where the point must be is a claim. The point D is trivially on the line AC from before, but the claim here is that it's between A and C. And I don't have any warrant or data for that here. So I might say there's a gap. It seems reasonable, and I think it's true if you drop, I mean, it is true that if you drop an altitude from the right angle in a right triangle, but when I was thinking about it in preparation for this, I'm like, well, there's some stuff going on here that I'd have to think about if I really wanted to justify that. So there's sort of like an implicit warrant that's socially acceptable, but maybe not fully justified. So then label the leg lengths, the length of the segment AD as S and the length of BD as T, and notice that it means S plus T equals C. The equals is a claim that S plus T equals C, and the data is how I've labeled the piece. The pieces, the warrant is not explicitly stated, but they're collinear, and so this is like the axiom of how length works. Right? If you have three collinear points, then the length from the first to the middle is plus the length from the middle to the third is the length of the first to the third, right? So they're the axioms of length in geometry. Now imagine, now this image contains three triangles, ABC, ACD, and CBD. Notice that ABC is similar to ACD because they both have right angle and they share the red angle. Right, so that's the data, that there are two angles that are congruent in corresponding ways, and then the warrant is a theorem that in the Euclidean plane, if you have two angles that are congruent, then the triangles are similar, right? And so on. So I believe, Drew, if you have the, you could post the link in the chat. to do resume recording. I was looking for the chat. Great. So if you're interested in this PDF, it's inside that link. So I will stop sharing and I will reshare again. But this time, this is the hub document that Drew just linked. You have access to my slides. You have access to that PDF that I was just walking through. So if it was too small, or if you'd like to see the whole thing for yourself with an example of an annotation, what I would like us to do now is I'd like to send you to breakout rooms to try to do your own Toulmin analysis in small groups. So you'll come to this hub page, and then based on your breakout room number, you'll go to these jump links. And if I were to jump to 6, there's a copy of a proof here. It's the proof that modular arithmetic is well defined. It's not framed that way. Multiplication of modular arithmetic is well defined. So there's a copy of the proof there, but if you'd like it in PDF form, that's what this link is. There's also a copy of it there. Inside each of these pages, I've given you a little table. You could do your analysis like I just did on the Pythagorean theorem, but my students often find it easier to sort of like pull out the first claim and then the associated warrant and data, etc. So let's go spend about 10 minutes. Drew, can you make relatively small breakout rooms?
How small is relatively small?
3, maybe 4.
Okay, this is 3 to 4. All right. Are we ready?
Yes. Everyone have what you need? Great. So go try this yourself and we'll come back and talk about it in 10 minutes. Sorry. Welcome back. Is that everybody? I think it is. Great. So some good stuff, some really good analysis. I just happen to be on group 11's right here. They identified the first claim is that there exists a K such that that equation is true. Their warrant is the definition of congruence, and their data is that that they knew they were congruent. And if you want to go even further, that they are integers / natural numbers where this definition may be applied. And then they sort of go a little further and they say the next claim is this equal sign. And one of the things I like about this is students start to realize why we lay out mathematical justifications in this way so that we can state the warrants off to the side, right? And we do this and my students are like, oh, now I get it, I finally see that. One of the things they struggle with is that the claim after this one for me is that this equals this. They are often tempted to say the next warrant is just what's highlighted, but that's not a claim, right? The claim has to be a sentence with a truth value. My students often struggle with that, which is part of the learning of this. But when we start doing this, they'll say things like, well, red. I'm like, red's not a claim. Apple's not a claim. This apple is red is a claim that could be true. True or false. Group 9 used the other approach, so we have some structure here. And there's lots of warrants and lots of, some of them are implicit. Do we have time? I think we do. Okay, so back in 2014, I taught this paper and a few others. Actually, let's go back to the pages. Okay, so when I teach this paper, it's a very challenging paper. You all have a lot of mathematical experience, and so you could make some meaning out of Toolman analysis. But for my students, this is quite a challenging paper. So how do I help them with that? First, we discuss that bizarre proof from the beginning. Often that, and sometimes we discuss things like if I promise that anytime class meets on Sunday, I will bring donuts. We have to sort of struggle with whether or not they accept that as true, right? I haven't broken my promise, so they sort of accept it as true, but otherwise they're very uncomfortable with statements whose if condition is false, how to deal with the truth value of those kinds of statements. So we sort of have this sort of more philosophical kind of discussion up front. Then they read the paper. they articulate some personal understanding of the meanings of the word, warrant, data, conclusion, sometimes backing, and I ask them to try to give small examples, and we talk about it. So they sort of like warm up on this idea before a discussion. And then they read the rest of the paper, and we often analyze. We'd spend longer than 10 minutes on it. We analyze in groups. They present their analysis to each other, and they notice some interesting things. I didn't hear any group notice it, but an interesting thing that often comes up is that there's communication stuff inside a proof that doesn't do any logical work. So it doesn't really appear in Toulmin's analysis, but they find it useful in other ways. But it's still a very challenging paper for them. So back in 2014, I had a group of students make a video about this. And they actually had learned 3 kinds of ways of thinking about proof. Toolman analysis here, another one about quantifiers, and another one that they call boring, obvious, clever, which is essentially the Selden and Selden formal rhetorical part versus the problem-oriented part of the proof. And then the video also contains a bunch of personal testimonials, like a "it gets better" kind of video. And the central example is exactly the proof that you were just working on. So let's watch a couple of minutes of their video. See if we can manage this. Share my sound and the video. Okay, so again, it starts with some testimonials. Then they talk about quantifiers. And then they talk about the formal rhetorical part and oh, maybe I've got this in the wrong order. Okay.
All right, one way to look at this proof is that there are 3 parts of it. There's the obvious part, the boring, and the clever.
Sorry, that was in fact the other part.
That AC is congruent to BD.
X-Files music, which I love.
Hi, discrete students. I'm going to show you how to use Toulmin's framework when solving proofs. First, we start with data. Data is what's ever given to us, whatever we've previously solved, anything we can use to solve the theorem. After that, we have warrant. Warrant's what we use to show why we can do things in the proof. It uses the data to come up with the conclusion. Backing is important because it's why we can use the warrant. And it's what makes the warrant actually valid. And that conclusion is whatever we come up with at the end.
L in integers, such that a minus b equals k times n, and that c minus b equals L times n.
So they're claiming that's the first claim.
Now the data for this conclusion is the first thing we need to find to solve the conclusion. And that is when letting n be in the natural numbers, and a, b, c, d be in the integers. This also means that a is congruent to b.
So it takes them about 8 minutes to do an analysis. I don't agree with it perfectly, but it's really useful to have near peers walk through this argument. So we might have a little bit more time later. And you have a link to that, to the video if you want to watch the whole thing at some other point. Oops. And so I use this video to help them prep. So between the sort of initial warm-up philosophical conversation and reading the paper, they engage the video. Sometimes I encourage them to watch the video before and after the paper, because it makes even more sense there. So if pause and let you have the QR code if you want, but it's in the hub document linked there if you want it. Okay, so contexts in which I have used this. I've used this in the upper division proof-oriented math classes, abstract algebra, modern geometry, and real analysis. So in those classes, they already have some experience with proof, and then we get a little ways into like building up whatever we're building together, and then this is sort of the tool that I use, like 2 weeks in to help them like really say like when we're talking about the proof, this is a way that I want you to sort of like attend to the details along the way. I have used it in Introduction to Proof, in that context, I spread it out a lot more. So like one unit will be about quantifiers, one unit will be about proof frameworks, and the third big unit will be about Toulmin analysis. So it sort of takes the arc of the whole course to talk about these ideas. A couple of years ago, I taught high school full-time. The Pythagorean Theorem proof said math 3 and 4 at the top of it. It's because that's the example that I gave my high school students before asking them to read parts of this paper. The paper uses real analysis examples, but you can engage them from a Calc 2 perspective. The meatiest example is a bounded monotonic sequence converges. So you can sort of frame that in a way that a Calc 2 student can make some meaning out of it. But I often have to substitute things in there. I have never used it with a Math for Liberal Arts class because I haven't taught that class in a long time, but Elizabeth Thorin uses this to help her Math for Liberal Arts students think about what the heck we're doing when we're making a mathematical argument, which she has found very productive. And this semester, I am teaching a capstone for secondary ed majors, and I'm using it to help them sort of reflect back on their previous experiences. Ideally, this would all be obvious to them, but part of the point of the capstone is to help them go back and synthesize their whole undergrad experience. And this has been helpful. Well, it hasn't been this semester, but in my past experiences, it's been really helpful for helping students make sense of previous proving activities. So just to get a little bit broader, what's happening in my current capstone course. A couple of days ago, we defined a sandwich. We spent a day defining sandwiches. The next day, we did a guided reinvention of the definition of approaching, like sequences as they approach infinity, as the index approaches infinity. And then we spent on Tuesday, we talked about quantifiers. So I gave them a bunch of sort of informal language statements like unicorns are real, or back in 2013, I had my cake and ate it too, and asked them to think about their logical requirements for justifying, negating, or using those kinds of statements. And then we sort of pulled quantifiers out of that. And then we used that to make sense of our definition of sequence convergence, essentially. And then today, in preparation for today, they read Selden and Bencalti paper about proof frameworks. And we use that to sort of start unpacking from statements into the structure of the proof. And next week, so I guess you can come back for an update if you want in a week or two. Next week, we're going to read this paper. So we're going to do some of that. We're going to talk about that cursed proof from the beginning of this talk on Tuesday, and then they'll read the paper and watch the video in preparation for Thursday. And then after that, in terms of this being a capstone course for secondary teachers, after we've thought really carefully about sequence convergence, we're going to go back and say, hey, that same idea helps us make sense of asymptotes, other kinds of limits, continuity, differentiability, integrals, and series. Like basically this one idea from analysis addresses all of these subtle reasons back in functions in the high school context. So returning back to my original claim that this is really important for sort of student authority, what are some things that that come up? A sequence of true statements is not a proof. Right, so that the cursed thing from the beginning is not a proof, but in particular, this is a very gendered phenomenon in my experience in Intro to Proof, where there's often a young man who sort of will say like, well, every single sentence I said was true. How dare you say that it's not a proof? And it's because we're thinking about something wildly differently. And this paper helps me talk with students about, I'm not saying anything you said was not true. I'm saying it doesn't convince, right, that we're validating rather than looking for the truth value. Another big thing that comes up and is mentioned in the Weber and Alcock paper is the transition words between sentences. Usually when my students read this paper, they're like, oh, now I understand all that feedback I got for the last 3 years, that I shouldn't start every sentence in my proof with and. Right, and so they finally get what we're trying to do, and they get that those words are cueing what part of the Toulmin structure the different phrases are, and they sort of they finally feel able to be intentional about that rather than sort of like throwing something at the wall and hoping it works. I think they start to see proving less as a magical thing that's like really super special in math, and they start to see that it's connected. So the fact that Toolman analysis comes out of rhetoric is useful, but it also, the experience of it feels connected. I happen to have been observed as part of my tenure process at my previous institution by a professor from the English department on the day that we were talking about Toolman analysis. And he's like, oh, good, I teach about Toolman analysis as well. And it was really useful to have the English prof who was visiting say that in class. Several years ago, I taught a very small class at the University of Michigan for a couple of days, and it was mostly incoming graduate students, but Deborah Ball also registered for it, which was a little terrifying. And we talked about this paper in this way, and she sort of said, oh, I've used Toolman analysis to help my graduate students think about the arguments inside their theses, but she hadn't thought about using it to teach students about proving. And so like that was really a really nice connection for me. It often turns out really powerfully that proof validation is socially constructed, and this is sort of the connection back to Kim's point from before. There is no well-defined algorithm that allows you to say for sure if something is warranted, right? And that is powerful for my students, but also sort of terrifies them. They're like, oh, the discipline that I was attracted to because I felt like this is the one where truth was absolute, like universal, objective, absolute. You're saying fundamentally this process of this thing we do is subjective, like at the core. That is a really powerful thing, and it comes out of this conversation. It's mentioned in the paper, and then it comes up in a conversation there. And then sort of the whole point here is we're saying as a community, this is one way we could decide if we accept arguments. We often do accept this way of accepting arguments as a group, but that it's a choice that a group of people make about how they engage with arguments. So this is sort of the beginning of saying to the students, like, you are participating in this action of deciding if you accept things. And the students always find it super helpful in terms of their future proving, that they're sort of saying like, oh, now I understand what I'm doing. Now my conjunction words are intentional, and I know how to string the ideas together. I can think, like, it gives them tools to think generatively about the arguments that they're constructing as they go forward. And so I'm perfect. I wanted to end with at least 10 minutes for us to talk about any questions you had, any other connections that you made, or any other things that came up as you tried to do some Toolman analysis together.
I have a question about something on that last slide.
Yes, this one?
Yeah.
Okay.
That's okay. Just
sure.
That where you talk about, say, proof validation is socially constructed. Absolutely agree with that. But where do you see proof assistance coming in that?
Proof what?
Proof assistance. So programs that validate check proofs.
Oh. That's an interesting question. I hadn't thought about it, but my first thought is that they have a built-in set of warrants that has sort of been pre-accepted, and so maybe socially constructed is not, maybe not the perfect word, but it's relative to a collection of accepted warrants.
Mm-hmm.
So maybe you have other thoughts about how I don't know how proof assistants are programmed well enough to say something more detailed there. Do you?
I don't probably know enough to myself, but I guess one thing you could say is that at least their warrants would be open to view, as it were. You'd have to be able to inspect them and be able to say, yes, we agree with these, or no, we don't like these, and they're not hidden away like, I guess, sort of more human mathematics often is.
Mm-hmm.
So in that regard, then they're possibly a good thing.
Yeah.
I mean, I feel like they solve a different problem because they don't, proof assistants can be really interesting and they can do really neat things. But if your actual goal is to convince a human that something is true, then they aren't necessarily the best way to go. They're more like the way that people go after they already kind of have a lot of insight into the language and the conventions and everything. And once you're an expert in it, you can also use them to explore new stuff. But, they aren't right now targeted at, convincing a freshman that an argument is true. Like you look at it and it's just bewildering. If they're much more for kind of like, they are, an assistant, not a replacement for kind of human, presentation.
Agreed, but I think they do have slightly more of a central role in that. I know I've come across proofs in the literature that are false, and sort of having had a proof assistant sort of run through them and pick those out and be able to sort of say, you can rely on these things. I don't know. I think I'd
making sure you didn't miss an edge case.
Yeah.
Yeah, interesting. Catherine, did you have something?
Did I have something? Oh, I think I was going to say maybe we should clap for our speaker, but I don't know. Thanks for the good talk. I can add a question, or I can add a comment and a question.
Sure.
I don't know if you had any experience talking with students about this sort of thing, but I find it very interesting to think about this also in the context of like, when you're reading like a paper, also, I think thinking about this sort of thing also really brings into context like things that you see maybe more in math papers than in the classroom, where you're maybe citing an unpublished work, or you're like, this major person in the field said blah, 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 or something like that. Like that's something that appears as well. I guess I guess if I had a question, it would be like, do you happen to know of a resource that has a list of transition words for students that describes their function? Because that's something that I'm sort of in the middle of producing. And if you had an additional resource to that, that would be interesting to me.
There are a few listed in the paper, but it's a very small list. I have found it very productive for the students to go back and look at all of the arguments that we've either done together or that was just analyzed and generate their own lists based on that. But I don't know of anything. It's hard because of phrase ordering in English. We sort of we play a little loose with this, and that interferes a little with students' ability to do that. But that's a good one. I'm going to take one from the chat first, and then Kim. There's some questions in the socially accepted and by whom kinds of questions in the chat, and I completely agree. I think I love how talking about this helps students realize oh, I sort of used to assume it was universal truth, and that it happened to be my instructor who was the one who told me it was true. But now I think of it as something that a community has accepted, and so that sort of opens that door a little bit in the conversation. In practice, in my own teaching, and I've never talked enough about this with other people to know if everyone else does this, but especially in my inquiry classes, I'm very careful about establishing what we have collectively accepted and what we haven't. So there's a big transcript that all of us, that we sort of put things into, and we sort of there's tentative things there, and then there's things that have been validated by the group, and then there's separate little transcripts that each group work has, and then there's individuals, and they have things that they think versus the things they believe versus the things that they sort of have definitely accepted. And so a lot of my work in a course is getting us to sort of come to some agreement about which things fit in which of those repositories. And so by being intentional about things like we believe this versus we've accepted this. I think I'm trying to locate that with the class community, but that means if I can't successfully convince them that something is something we should accept, then things get dicey sometimes. Yeah, Kim, you had a question. Work on it.
Yeah, there's a significant difference between this model of a proof where you have dates being the main thing and then the connectives with the warrants being also secondary structure, versus if the warrants as connectors seen as the primary structure operating on the data, like you're, I don't know, laying down Pokemon cards or something that have these operations signed by the warrants to modify what you've got available. Do you work with any structure where those connectives are the primary objects of the proof? Do you see what I'm getting at there?
I'm not sure I fully understand. I think I agree that I see a lot of the hard work in helping undergraduates think about mathematics the way we seem to want them to. Is helping them attend to those kind of registers, right? Register in terms of like, you know, an aspect of language and or maybe abstraction in this case. And yes, I think that I'm trying to help them attend to that, but just like group theory is really hard at first because you're used to thinking about particular objects and then suddenly the thing you're proving about is an operation, which is not an object. Exactly those connectors being the objects of study is really hard. So I'm trying to get us there, but I'm trying to do it in a way where I don't say, well, let's define a logical connector in this way, and therefore we're like, I think I could, well, I'm sure I could crush some young people if I weren't careful going in.
Okay, I'll try not to do that when I'm in yours.
Great, thank you. Benjamin, you have a hand up.
Thank you. Yeah. Here, I'll put my hand down preemptively. So I'm very excited by this presentation. I've seen you talk about Toulmin Analysis online and stuff, and I was excited about that too. Like, it seems like a very powerful framework to use with students to kind of make the work of reading and writing, but especially to me, it seems like reading proofs explicit to people who don't already know how to do that. I'm soon going to be working with students that are completely new to this whole domain of academic labor. And so I'm kind of excited to incorporate these ideas into my proof instruction. Historically, my approach to proof instruction has been about what centered on students' sense of what forms conviction for them. So it's been very like organic, you know what I mean? I instruct students to attend to their own sense of conviction very carefully and have that be kind of how you tell the difference between something being successful as a proof and not. But on the other hand, compared to this, very unstructured. Like, this is like a very concrete set of what's the warrant, what's the data is very regimented set of questions to ask. So I'm having a little moment. This is a kind of free form question. I apologize for the free formness of it, but I'm like thinking through how am I going to integrate what I've found successful in the past, which is really good at staying close to the truth of the student's heart about what they buy and what they don't buy, with something that I'm very excited about because of how it makes the work explicit. I just love the way it's showing that, making very explicit for students, you have to find the warrant. It's like, oh my God, yeah, that's the main thing I do when I read proofs is I look for try to infer the warrant. Mm-hmm. So I'm excited by it. And I'm just thinking through how to integrate, and I'm curious about your thoughts about that.
We could go on for a really long time, but I would love to read the proof schemes paper with students, the Herrell Sauter, or Soter, I always forget how it's pronounced. And I do often read Perry's scheme of epistemological developments to help them sort of name the ways they're approaching things. But I think in practice, what I do is I have to problematize these epistemological issues. I don't just insert this. So we sort of like, once they get to the point where they're like, I mean, I feel okay about this proof, but I just don't know. And I'm frustrated that I feel like someone else has to decide for me. Then I'm like, great, I set you up for that. Now I have a tool that you might be with. So like, you know, if they come in very empirical, working with some things where that works, but then where our intuition falls apart because it betrays us because we didn't check all of the examples, and then that makes us want, so like I'm engineering situations where their current epistemology develop, like where they notice the cracks in it, and so that we can sort of introduce other kinds of things. I completely agree, it has to build from where they are rather than just saying do it this way. That's critical. But we don't have time to talk about every hour of class at the depth of 3 hours of talking. So that's perfect. We're about out of time.
Thank you.
Matt, I'm happy to stay around and answer, but I think we might have to end our recording. Thank you. This was fun. I'm planning to write something about this so that it's in a less, I don't know, a more focused domain.